Good morning, everybody. Afternoon. No, it's not afternoon. It feels like afternoon. Today, are you guys feeling pretty high energy?
No.
Yes.
Okay. So I'm feeling really high energy. I got two other really big presentations I have to do today to other groups of individuals. So I feel like we're gonna do this. We're gonna make sure that everyone by the end of the day is able to draw Lewis structures and know their polyatomic ions, at least some of them. So we're going to spend some time working on that. You guys have already had some practice, and you may even say some frustration going into lab, feeling unprepared, working through stuff that you don't have training in. So that is somewhat intentional. I think one of the best ways to learn and to be open to working through material is having struggled with it yourself. So I'm sorry if you're not happy with that, but I think that at the end of today, and especially at the end of Monday, you guys are going to feel really good about working through Lewis structures, exceeding the octet rule, all this kind of stuff. So we're just going to dive right into it today. So in drawing Lewis structures accurately, that means that you'll be able to determine the steric number, which hopefully you guys have been working with some, as well as the AXC representation, which you might not have heard of yet. You'll need to be able to calculate the formal charge of every single atom within a molecule, and then use that to identify when more than one structure is possible. And then from that, you'll be able to determine which resonance structures are most stable and accurate. We may kind of have some side conversations about strength and length of bonds as we do this. We will continue that conversation throughout the entire year, so this will be a common theme for the class. Have I asked you guys to memorize much yet? Okay. A huge part of my philosophy, and there's a quote by Einstein that supports this, so it must be awesome because Einstein thought it, is why memorize something when you can look it up? That is true for a majority of chemistry. If you can look up a term or an equation or something like that, you don't necessarily need to be able to memorize it. That's why I give you the note cards in the exam. There's one thing that a couple things throughout the year you'll find that I do require you to memorize, and the reason is because the language of chemistry, if I say something, carbon, for instance, you need to know something about that immediately. I'm not asking you to memorize the periodic table because you learn that as we use it, and we're going to be using it a lot. Polyatomic ions are ones that we use a little less frequently, and so I'm going to ask you to really spend some time memorizing, making note cards, doing whatever it is that you need to do in order to memorize table 2.4 in your book. When I say nitrate or nitrite, I need you guys to know the difference between those. I need you to be able to draw the Lewis structure. I need you to know how many charges are in the different atoms. So this list right here is a really good place to practice with the approach that we're using today from the Chem Tour that you guys have all completed surely by now because I've emphasized it so many times. If you have not yet, then you'll get practice today and then you'll get to go do it this weekend. So I need you, it's not a huge list. Honestly, most books have a list 3 times this size of polyatomic ions. There are a lot more. And I need you guys to be able to recognize when I say hydroxide what that means. Sulfate, sulfite, chromate, dichromate, chlorate, all these different things, okay? We're going to be using these a lot throughout the course of the semester, and I need you to be able to access it quickly and not have to go look up some of these things, okay? What do you think that means about your note card for exam 2? There is one rule on exam 2 that you can't have polyatomic ions. And I think I include strong acids and bases in that if we get to acids and bases at that point. So there's a restriction to the note cards. We will be checking them before we start the next exam that you don't have polyatomic ions written on there. And if you program in your calculator, is that okay?
No.
No, that's not cool. And actually for the next test, I'm going to see if I can borrow a bin of graphing calculators and have those available for you to check out for the exam. Because I would ideally not have you use your own graphing calculator, but use one that we provide you just so there's no programming things. That's what the department has asked me to do. If I have that capability, I think I might have access to those calculators. There'll be TI somethings that will be like your graphing calculator.
Could we still use our own if we don't have a graphing calculator?
Yes, if you don't have a graphing calculator, it wouldn't matter. Okay. Any questions on polyatomic ions? All right, so let's just get right into it. I want you guys to use this approach, S equals N minus H, to draw your Lewis structures in this course. It's going to give you a starting point for what your Lewis structure should look like. From there, you might make modifications. if there's something that's in period 3 or higher. And you guys have probably already talked about that, possibly in your lab when you looked at some sulfur-based compounds. So this S equals N minus H, I think this is the same terminology that your chem tour used. The way I think about this equation is a lot of times we want to know how many bonds are in a molecule. How does the number of shared electrons relate to the number of bonds in a molecule? Can I get a hand raised? Volunteer. Shared electrons relate to bonds.
Like, okay, so for example, don't if you have like 6 shared electrons, you divide it by 2 and you get 3 bonds?
Okay, so each bond typically has 2 electrons. Okay, so last class we talked about energetics of forming and breaking a bond. Why do atoms form bonds? Why do they form what we call covalent bonds? Talk to your neighbor about that real quick. Let's summarize from last class. Why do atoms form covalent bonds? All right, can I hear someone's discussion? Why do atoms form covalent bonds? Rudy?
So they can be more stable.
So they can be more stable. Okay, great. Can anyone elaborate on that as well? Kevin?
So they can have a full octet.
So they can look like they have a full octet. And a lot of times you say they have a full octet. That fruit fly attacking me. What we'll start talking about today is that it actually looks like they have a full octet, but a lot of those electrons are mimicking one of theirs by being someone else's electrons, and so how we count those electrons is going to be important. So I'm going to say for the sake of today that they don't actually have those. They are sharing in order to look like they have an octet, which is a much more stable configuration. So I love going to stability as the first descriptor there. Okay, so we're going to try to find how many shared electrons we have. And remember, if one electron is shared from each side, that means it's going to be a pair, and that's a covalent bond. And then sometimes we have 2 covalent bonds between an atom. Sometimes we have 3 between 2 atoms. So knowing the number of bonds helps us think about what the structure is. So if we can find the number of shared electrons, we can find the number of bonds. Okay? In order to do that, we're going to practice on CO2. And this N in the equation stands for, if every element had its stable number of electrons, how many would that be? So I call it number for N. I'm not sure exactly what they define N as. So if we have carbon, what is N? 8, because it would have an octet. If we have hydrogen, what is N? 2, because that would look like helium and have a full configuration. What about phosphorus? What would N be for phosphorus? 8. Basically, if I ask you anything besides hydrogen, it's going to be 8.
Even boron?
Even
boron, I felt like...
There's an exception with boron.
Okay.
Yes. Great. There are always exceptions in chemistry, so thank you for pointing that out.
I wasn't sure. That came up in the homework, actually.
Yeah,
so.
absolutely. Great. So that is one of the very few exceptions. And then this H. H, as I call it, how many they have. And how many electrons, when we're talking about bonding, do we say that carbon has? 4, because it's in group 4. What about nitrogen? How many electrons does nitrogen have? 5. Okay, so what type of electrons are we referring to when we say how many they have? These are our valence electrons, okay? So this equation is relatively simple. So basically what it says is, in our molecules, we have a certain number of electrons. Those don't add up to enough for every atom to count as if they have an octet on their own. It doesn't work. They're not all noble gases. If we had all noble gases, we're not going to form many bonds. There's crazy things that happen in chemistry, but for the most part, we're not going to form bonds. So if we want to know how we have these atoms together, increasing their stability, then a lot of those electrons that we have are going to have to be counted once by one atom and a second time by the other atom. So this equation basically says how many of those atoms get counted twice in order to make up the difference between what we actually have and the number that would be ideal for the noble gas configuration or the more stable configuration. That's what this number gives us. And then from that we can say, well, If there's 10 electrons that we don't have that we should have in order to have that stable configuration, then we have 5 bonds. Okay? So let's go ahead and do this with carbon dioxide. We're going to need to do a few questions to kind of build up to it. So let's first start out. What are the total number of valence electrons we have in carbon dioxide? Go ahead and click in your answer. Once you click it in, you can check with your neighbor. What do you think we have? 40 today? 45? Raise your hand if you need a couple more seconds. Okay. All right, getting close. So what if I say that we have 10 valence electrons in this molecule? What mistake did I make? Can I get a hand raise? Joey. I didn't count oxygen twice. So in this molecule, what we're going to work with, and you guys have already been doing this some in lab, is that each carbon dioxide has 2 oxygen. That's what that little 2 down there refers to. So in order to determine how many valence electrons, we need to count the valence electrons for carbon once, the valence electrons for oxygen twice. And 87% of us got there. So we have 16 valence electrons in CO2. And the question is, where are they going to go? How many of those are going to be used for bonding, and how many of them are going to be used for other things? So I have this table, and if you look at your worksheet from last class, you'll see that there's one of these as well for nitric acid, HNO3. And I highly recommend you go back and practice this on that worksheet as well at another time after class. We'll be using the results from S equals M minus H for that today in class. Okay? So if we're looking to fill in this table, why don't you guys go ahead and fill in the rest of the table? So what would the octet or duet be for each of these? How many valence electrons do we have? And then let's look at the total for the N and the H. And then I'm going to ask you some questions based off of that. We'll fill in kind of the next few questions below it.
It's like a really awful brownie moldy issue. Everyone that has blonde hair that I've seen.
Okay, so let's go ahead and fill in this table. What do we put here under the octet or duet number for carbon? 8, sounds good. And there's one of them, so 1 times 8 is 8. What about how many electrons carbon has? We said that has 4. Okay? So that is just 4 in the H. So we come down to oxygen. How many do we put in the octet N for oxygen?
16.
Is it 8 or 16? 16, because we have 2 oxygen atoms. Each one is striving to get a full octet to increase its stability. Nope, not at all. Yep, it's all about what we're going to get to the totals down here. And then what about the H? How many valence electrons do we have? 6 for each oxygen atom. Then we have 2 of them, so we have 12 valence electrons. I think I had this filled out. So then our totals, we can add up those 2 columns. We have 24 is the ideal number of electrons that those atoms need to be stable in a molecule. We don't have that many, right? We only have 16. So the question is, how many of those 16 need to be counted twice in order to make it look like we have 24? And that's what our S is going to be. So how many is that? How many shared electrons do we have in CO2? Go ahead and click in the shared number that you calculate. You can either do it 2 ways. You can do it mathematically, just using our equation, because we have N and H down here. Or you can say how many of those the 16 electrons need to be counted twice in order to look like we have 24. One is logic, one is calculations. I'll give you the same answer. All right. I guess I want to share their answer. What do we got? Is this easier just to pull up because it's math? All right, so we do mathematically. We do 24 minus 16. We get 8 shared electrons in this molecule. So I agree with you guys. And I don't know if I can click the correct answer. Woohoo! By the way, when I grade it, it just is to show you guys that's the correct answer. There's no more credit for the right answer or the wrong answer in this class. Just to reiterate. Okay, so then we have, using S equals N minus H, 24 minus 16, that's 8 bonding electrons. So then, we don't need to click this in, I imagine. Every bond has 2 electrons. So that means that we have 8 bonding electrons. We divide that number by 2, because each has 2. And we have 4 bonds. Okay. So then let's go back and let's think about, we have 16 electrons, right? How many leftover electrons do we not use in bonding? Go ahead and click in your answer to that one. How many of those 16 electrons are left over and were not used in bonding? Couple more seconds. All right, so our biggest answer to that question is 8. Can someone describe how they came up with 8 leftover electrons, Caleb?
I just thought of it as like the little dots you put around the atoms instead of the actual bonds when you draw a structure.
Great, so that's what we're going to do with them, is we're going to take those and draw them around the structure instead of having them as the dots between atoms or the lines between atoms. Ruby?
I just did the total valence, which was 16, and then subtracted the number of shared electrons.
Great, so we can just take 16 valence electrons. We know how many we have. We know that of those 16, 8 of them are going to be shared. So the other 8 are not being bonded. They're not shared. So let's go ahead and draw our Lewis structure. So on your page, go ahead and write out the 3 atoms in CO2. Draw that structure with 4 bonds. And then figure out where to place the extra 8 electrons. Do we put the electrons one at a time, or how do we put them around the atoms? 2 at a time, and we call those lone pairs. So take those extra 8 electrons, figure out where they go around the individual atoms. Make sure that no atom has more than 8 electrons around it, and we'll talk about how to determine that in a second. think about your molecular shape if you have that.
So is there a number you add the number of bonds that you make plus the number of electron pairs?
The number of electron domains. Single bond counts the same as a double, counts the same as a triple bond. Counts the same as a lone pair. So I have two structures, Lewis structures drawn up here on the board. I want you to select which one of those you think is the best, and then talk to your neighbor as far as why. So think about the lab that you had this week. And if you have, what's your steric number around that oxygen?
It's going to be, like, you talking about the charge or the...
No, the steric number. So how many electron domains are there around that atom? So double bond counts as one, lone pair counts as one. So how many?
You got four, right? So you got two lone pairs and two bonds?
Double bond counts as one.
Oh, okay. So
Triple bond counts as one. Yep. So if you have a steric number 3, you have 3 domains of electrons around that atom. Where are they going to be in space? Think about the molecular shape that we talked about before.
structure.
Okay. All right. Has everyone got a chance to choose which one of these two structures they think is best? Are you guys in agreement? Let me see if I can pull up and see what you guys are doing here. Usually I can see the results on a little base, but with this cloud-based one, I actually have to pull it up on my phone. You guys are in a pretty strong agreement. I'm going to make an argument that both of these structures fit a lot of our rules. What rules? So one of the rules we have is that we're trying to make it look like every single atom has 8 electrons. Does that apply to both of these structures? Yes. Okay, the one on the right, it has 6 electrons of its own, 2 shared on that oxygen. The carbon has 4 bonds, so that's 8 electrons. The oxygen on the right has 3 bonds, so it's 6 electrons and 2. Totally fine. Do we have the right number of electrons, the total number of electrons? We can only work with the 16 electrons we said we have. Do both of them have 16 electrons? Yes. Great. So then why are these not equal? Moed?
There's charges, I think. So on the right side.
What kind of charges?
If you so oxygen is supposed to have 6 valency electrons, and over there it has 1, 2, and then 3 shared, which is 5. So it has a negative 1 charge. Okay, so we're going to get into how to calculate that in 1 second. So you use the term, you brought it back up, formal charge. And so I want us thinking about what the formal charge looks like for every atom and every Lewis structure we draw, and that's going to drive which Lewis structure is ideal. Okay? So the way that I draw formal charges might be similar to what you did, or it might be very different. And the boxes kind of help denote that. So whenever I draw a Lewis structure, a lot of times I'll go ahead and just draw a circle. And so I'm going to circle one atom at a time, and I'm going to do what Moed was describing. So formal charge is a description of how many electrons does each atom own compared to the valence electrons that it brought in, which is, I think, pretty much what you described. So if we look at these, the oxygen atom on the far left that's inside the circle, this oxygen atom obviously owns the lone pairs. Nothing else is competing for those. Those are all its own. So that means that oxygen has 4 electrons on its own, and then there's 4 electrons, each one represented by a line for a bond, between that oxygen and a carbon. So it gets to count half of those. It's kind of like the United Nations. Everyone gets to count half of what's there. Like, we're nice and diplomatic about it. We'll get into oxidation numbers later, which is not like that. That's much more like a dictatorship. So we have 6 electrons that it gets to count. How many electrons should oxygen have based on its valence number that it brought? 6. So it's a formal charge. The difference between those, so it has a 0 formal charge. What about the carbon? We do the same thing for the carbon in the middle. We'll go ahead and we'll circle that. The reason that I circle it is to cut those bonds in half. It helps me remember how much of the electrons I get to count for each of the atoms. So if we look at the carbon, how many electrons on the left does it get to count? One from each of the one from each of the bonds, so it's 2. On the right side is 2. Total of 4. It should have 4. So the formal charge of that oxygen, or the carbon is. And then we'll do the same thing on the far right one. We have 2 lone pairs, so that's 4 electrons. It has 1 from each of the bonds. That's 6. Should have 6. So formal charge is 0. Yeah, I hate the equation. It's just like memorizing and plugging things in. Okay? So I'll do one of the 3 atoms on the right, and then you guys should complete the rest on your own, just to make sure we're on the same page. So if we circle that first oxygen, how many electrons does it count? 7, because it has 6 in lone pairs, and then 1 of the bonded. It should have 6. So that means it has 1 more than it's supposed to. That's a -1 formal charge. Remember, electrons are negatively charged. It has 1 more of the negatives than it's supposed to. So go ahead and do the same for carbon and oxygen in that right structure. Talk to your neighbor to compare and make sure you have the same formal charge for each of those atoms. Anyone need another? Raise your hand if you want a little bit more time to determine the formal charges. Okay. Get another 20 or 30 seconds. And let's do this shorthand. Let's do 0 formal charge is thumbs sideways. +1 is up. -1 is down. Does that work? So for the carbon, is it neutral with a 0 formal charge? Is it positive or negative? See, almost everyone pointing sideways. Okay, so let's do the circle method. We circle through it. Gets to count 1 from each of the 4 bonds. That's 4. It should have 4 valence electrons. Those match, so we have no formal charge. All right, what about that oxygen on the right side? Thumbs up, positive charge, neutral, sideways, thumbs down, negative. All right, almost everyone is pointing up. So if we circle around that oxygen there, how many does it actually get to count? 5, but it should have 6, so it's missing a negative, which makes it +1. That's the formal charge of that oxygen. Okay, so go back to answer this question. Which one of these 2 structures is better and why? Eric, you want to describe why? A is better?
Well, because B would have a polarity.
So polarity is a bit different from formal charge. Sarah?
Well, isn't oxygen only supposed to have 2 bonds, and plus A has 0 formal charge?
Okay, so we'll get into how many bonds. I want you constantly thinking about how many each atom typically has, but that does not mean it has to have that many. It means it's most commonly, oxygen is almost always found with 2 bonds and 2 lone pairs of electrons. But if it doesn't have that, it means there's going to be a formal charge, and that's okay. If we have an opportunity to have a lower formal charge, we're going to take it. It's like saying if you have water in a fish tank, it's going to find the most stable place. It's all going to be level. You're not going to have water that's stacked up on one side and then missing on the other side because there's a more stable configuration to get to. So formal charge I think about kind of the same way, where if we have an opportunity to have that lone pair of electrons moved over, maybe I'll draw this out how I see this. So if we have, oops, there's not an oxygen in the middle, huh? If we have this structure here, what we're saying is that we drew one of the lone pairs on the far left side instead of the right side. And so I can circle that lone pair and I can say, well, maybe that lone pair should actually be bonding to carbon. And that bonding should be a lone pair. Organic chemistry is all about pushing electrons. I don't know if you've heard that term before, but it's about seeing where electrons can move. If we move these electrons here, carbon has 5 bonds, which is a cardinal sin in chemistry. Carbon will always have 4 bonds, unless it has a positive charge there. You won't see that in general chemistry. Organic, you'll start to see carbon with 3 bonds. It is a fleeting moment you'll see that species. It doesn't stick around very long at all. It's very unstable. So I want you to justify which structure is best because of the formal charge that has the least number of charges or the lowest number of charges, if there's a way we can rearrange those electrons to be more stable. There is, I think, a table here that kind of walks through the calculations. I'm going to post these slides afterwards, so if you forget exactly how we did it, it's exactly what we talked about by the circle method. We have 6 valence electrons. 6 electrons are assigned to that, so the formal charge is 0. And then kind of go across like that. Yeah, Joe?
So what circle method don't work? What if you have to actually write it out and do the math?
Say again?
What if you have to actually write it out and do the math because the circle method don't really make sense to you? It's easier.
There are equations that you can use to do that. If that makes more sense in your head, that's fine. You just need to be able to come up with the appropriate formal charge. Yep, so I'm showing you the approach that works best for me. And equations, I think sometimes you can get lost in the numbers and not think about what it means as far as distribution of electrons. So make sure when you do the calculations, look at what that means for distribution of electrons as well. Question, Kayla? No. Okay. So as I mentioned, your last class's worksheet has nitric acid, HNO3. So I would advise going ahead and doing all these questions for that as well, figuring out how to justify the Lewis structure you're about to see, because I'm trying to decide whether this is worth class time or not. So what I'm going to do, I think the way I have it written in your worksheet, is I'm going to tell you the results of S equals n minus h. I want you to go back and verify it on your own as practice. If we do S equals n minus h, we have these atoms for HNO3, and these are the 2 outcomes. Go ahead and draw the Lewis structure for nitric acid. I think this is question 10 on the back. It's a very quiet room, so talk to your neighbor, see what they've drawn, how it compares to yours. There's a lot of different ways you might try to draw this. Talk about how to identify the best.
Oh, I don't know what that is. I'm not sure.
HM03 does. But it's a really good observation. That's cool. I'll mention that. If I forget to mention that. Yep. Take one more minute to compare, and then we're going to talk through this. I see very few pluses or minuses on your paper. You might need that to argue your case.
Single bonds to nitrogen and oxygen below. One more and single electron.
Okay.
Double bond on the right.
Oh yeah, it normally has it, yeah.
That's probably where. Right. Another 2. 1, 2.
All right, let's bring it together. I saw a lot of ways of drawing this, and I'm hoping that after comparing with your neighbors, you were able to come to some sort of consensus around which one might be better or worse. So let me draw some of what I saw. I think what I wanted to draw was this. This is one of the things that I drew. What are one of the drawings that I saw? What's the formal charge of each of these oxygens? Formal charge. I hear a lot of numbers all over the place. All right, so if we were to circle around this oxygen, it gets to count each of the lone pairs, so that's 6. It gets to count 1 from the bond, that's 7. It should have 6. So that's a -1 formal charge. So I'll go ahead and use orange. -1 on that oxygen on the left, the one on the right as well. We start to see a lot of patterns that every time we see oxygen, we start to recognize, oh, if it has 2 lone pairs and 2 bonds, it's 0 formal charge.
If it has 3 lone pairs and 1 bond, that's going to be a -1 formal charge. And you start, as you do this over and over, and you do more repetition, it comes a lot faster. What about the nitrogen? What's the formal charge on the nitrogen? I hear +1. It should have 5 valence electrons. It only gets to count 4, so that means it has a +1. What about the oxygen connected to the H? 1 from each of the bonds, so that's 3, 4, 5. +1. We didn't talk very much about electronegativity. We will some more next week. You never, almost, if you have the option of, that's a bad statement to make. Very frequently when you see oxygen, it's going to have a negative charge on it. There are opportunities where you see positive, but that's much more rare. So that's kind of usually a red flag. And like, ooh, is there any way I can get rid of that and not have that positive charge? What about the hydrogen? 0. Okay? What are some other ways that we drew this? So right now we have 4 atoms with formal charges. Did anyone find a way with less formal charges than 4? Aaron?
So I put 2 double bonds on the oxygens on the right and left of nitrogen, and then on each one of those I put 2 lone pairs, and then between nitrogen and oxygen on the bottom I put a single bond and 2 lone pairs, and then between oxygen and hydrogen I put a single bond.
Okay. How many electrons do we have total, and is this the right number? I can't remember.
We need 1 more. No, that's
I think we're 2 electrons short, is that right? Or do we have the right number of electrons? So we know the total number of electrons because we have 1 hydrogen, 5 from nitrogen, 3 from each of those, so that's 18, 19, or just 24, right? We should have 24 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, great. What are our formal charges?
0.
All zeros all the way around? So one of the things that we're going to come across is, does everyone obey the octet rule? And so we can't do that. Nitrogen, so the octet rule has to be obeyed by everything in period 1 and 2. That means you can't have more than 8 electrons that are attributed to any one atom in the shared model. So that nitrogen now has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can't do that. Did anyone have a slight variation of this? Moab?
You put you change the hydrogen from how, you know how the original model, or how you drew it out, it's connected to the oxygen that's double bonded. You put, you use a single bond with hydrogen and one of the oxygens that have a single bond on the right side.
Okay, well, there's double bonds on them. So I'm going to take what you're saying as... I don't know that we need to move the hydrogen. Let's try this instead. What if instead of... So we had the right number of electrons, but we can't have 5 bonds to nitrogen. We can only have 4. So what if instead of that pair of electrons being bonding, we move it over to be on oxygen? What happens to our formal charges now? So on this oxygen on the top right, what's our formal charge? The nitrogen in the middle?
+1.
Is this better than the first structure that we drew?
Thank you.
Why?
The oxygen doesn't have a positive.
Nice and loud.
The oxygen doesn't have a positive formal charge.
So we have 2 atoms that don't have formal charges that did before. Right? We only have 2 instead of 4 atoms that have formal charges. So this is a little bit more of a challenging Lewis structure. This is the best Lewis structure that we can draw, and it does have some resonance structures we'll get into. Aaron?
So that's the one that I started out with first, but when you're calculating formal charges,
It doesn't have as nice formal charges, but we can't break the octet rule in order to get better formal charges. If we're in period 2, we can't do it. If we had phosphorus instead, we could.
okay.
Or sulfur. And so what I want to start to think about is that anything in period 3 or below does not always have to obey the octet rule. Sometimes it will, but we have the opportunity, if we can decrease the formal charge, of moving electrons and actually having 10 electrons attached to that atom. And sulfur and phosphorus are the ones we'll see most often.
So that's incorrect and it doesn't have the charges on it?
So I did not draw the charges on that structure there because we just drew them out. So if you're to draw the appropriate structure, the best one is to have a plus on the nitrogen and a minus on the oxygen. What's the overall charge of that atom, or that molecule, sorry? We have a +1 and a -1. It's a 0 formal charge. And we'll notice that that is the exact same as the formal charge that's for the formula itself. If we had a negative charge overall, those two have to match. For instance, I had some people ask me, how do I know the hydrogen's not attached to the nitrogen? And the reason why is because as we learn our polyatomic ions, we know that we find clusters of atoms covalently bonded very frequently in nature. One of them that we find really often is nitrate. So as soon as we see NO3 in any structure, we automatically think that's going to be a cluster of atoms that are together. And if we draw that Lewis structure, which is worth practicing, what we'll find is that we'll have 2 negatively charged oxygens and 1 positively charged nitrogen. That hydrogen is not going to be attached to a positively charged nitrogen. And it's actually an H+. If we combine these two things, that is nitric acid. So what we start to see is patterns, and this is one of the reasons I need you to know those polyatomic ions. We're going to recognize them really quickly. We're going to say, okay, I can draw the Lewis structure for that. Something is attached to that Lewis structure. In this case, we draw it as a covalent bond. In reality, it's more ionic than covalent, but we'll spend some time on that next week.
For the naming of them, so like that one, do we say hydrogen nitrate or do we have to say nitric acid?
There's going to be 6 acids. You'll have to say the formal name. And we'll get into those. So we have just a couple minutes left. What's the steric number on nitrogen? Think for yourself for 10 seconds. The steric number. Actually, go ahead and determine the steric number for each atom in this Lewis structure with the charges on it. On your paper, write down what the steric number is for each one of those. I think those questions are written there. Yeah, it's part of question 10.
Or the AXE notation.
Not yet. All right, so let's go around. Top left oxygen. What's the steric number?
Oh, no.
3. Why is the steric number 3?
Oh,
Double bond is 1 domain of electrons. You guys saw this in lab this week.
yeah, we did.
Have you added? Did you mess with double bonds and add those? Maybe you didn't mess with that. Okay. So in lab, make sure to try adding double bonds. Do this PhET simulation on your own. That is the same approximately as a single bond as far as Vesper theory. So we have 3 around the oxygen on the left. Nitrogen.
3.
Steric number 3. Oxygen on the far right. 4. Oxygen here. And hydrogen.
1.
Okay.
So I guess the steric number is just the number of the cluster of electrons?
It's a number of electron domains. It's a kind of simple way to describe that. So it doesn't matter if it's a lone pair, single bond, double bond, triple bond. It's how many of those clusters or domains are around that atom. All right? And then the last thing we're going to do is the AXE notation. Here's the 3 AXE notations that exist describing some of the atoms. I want you to determine what it is for this oxygen. You have a question, Dawson?
Yeah, would the steric number for a chemical formula be like all of them?
I haven't thought about that as far as the entire cluster. I'd have to look at that. So what does the AX and the E stand for? If we're saying that this one right here, the oxygen in the top right, A, X1, E3, what did the X's stand for? For this one, it has one X. What's the X?
Bond. Single bond.
How many bonding domains it has? What is the E?
Lone pair.
Number of lone pairs. So if we do 1 plus 3, that's a total of 4 domains. Steric number is 4. Steric number is really blunt in saying there's 4 domains. I'm not telling you what they are. AXE is a way of representing that one of those 4 domains is bonding, 3 of them are non-bonding, lone pairs. Oxygen on the top left. It has 1 bonding domain, 2 lone pairs, AXE2. So think about what it would be for the rest of the atoms. We're going to start class on Monday, doing some of the description of why it is that we exceed the octet rule. There's the homework due Sunday. We'll have a post quiz due on Monday. I'll open it Sunday. If there are any questions you feel you are unable to do, please post questions to Blackboard discussion.
Are you gonna ask me to go?